welcome back to your Module 1, Simple Stress. Okay, so we will proceed with your Unit 3. Okay, in your Unit 1, we discuss about normal stress. Unit 2, we discuss about your shear stress. And now we will proceed to your Module 3, or Module 1, Unit 3, which is your bearing stress. Okay, so in this unit, this is our learning outcome. So first is for us to compute for bearing stress, and then solve for normal, shear, and then bearing stress in a problem. So we will try to first introduce ourselves with this bearing stress. Okay, let's define by means of the formula and by means of an example, and then later on let's try to mix that one together with the normal, shear, and of course this bearing stress. Okay, so first is, what is bearing stress? Okay, so if you say bearing stress, okay, to differentiate that one from compressive stress, which we discussed in your as a part of your normal stress. Okay, if you say normal again, that could be a tension stress or it could be compression. It depends on the force, if that is a compression force or tension force. Okay, so to differentiate your bearing stress from your compression stress, the bearing stress is a contact pressure. Okay, contact pressure between separate bodies. So this type of stress is developed due to contact of two different bodies. So what are the examples of this? Example of bearing stress are, for example, you are considering a soil pressure beneath piers, or if you say piers, that could be a footing, okay, or foundation. Let's say this is the foundation, this is the soil. If that is in contact, the footing will be carrying the load from the building, isn't it? Let's say that is a footing of a building, and then that will be transferred to the soil, and the stress developed between the soil and the footing is what we call as the bearing stress. Okay, and relating that one with most of our examples, which is on connections. Okay, one example of bearing stress also could be the force on bearing plates. Okay, bearing plates. If you say bearing plates, those are the steel plates. For example, you originally have there a concrete column and you're going to connect a steel column. Okay, you're going to make it a composite column. Then for you to connect that, let's say the shape of that steel is I shape, and then the column of the concrete is rectangular, so you need to connect that one, okay, thoroughly, so that that will act as one. So how are we going to connect this steel from your concrete is using what we call as these bearing plates. Okay, so you are going to put their plate, steel plate, on the shape of the rectangle or of the concrete column, and then that is where you will attach your steel by means of bolt or by means of welding. So what else is we can consider there also the pressure between the axle and its bearing. Okay, that could be bearing stress, or it could be the rivet and then with its contact surface. So as we will go on with the example, we will try to have this explanation. Okay, just like example of the bolt and then the contact surface of the plate. If you are connecting members using bolt, then you can have there what we call as the bearing stress. Okay, so in here, in the next slide, as you can see, this is the example of bearing stress on bolts or rivets with the connection. So, okay, you can read about this. We will denote your bearing stress, since actually bearing stress, we are referring here to a compressive, okay, compressive stress. But to differentiate that one from your normal, let's try to use a subscript B. So our bearing stress is denoted by sigma B. Okay, sigma sub B. So for example, look at this connection. Let's say this is a lap connection. Let's say that is a member to members steel plate, which you will be joining using this pin or bolt. Okay, so you're going to connect that one by using pin or bolt, and then once you will try to exert an effort between these two different members, of course that will create an stress on the bolt connecting these two. If you are considering the stress experienced by the cross section of the bolt, that is a shearing stress, isn't it? That is a shear stress. We discussed that one in unit 2. But if you are referring to, okay, going back to the figure here, if you are referring to the stress within the connection or within the surface connecting the bolt and the plate, then that is what we call as the bearing stress. Again, bearing stress is developed because of the contact of two different bodies. So the two different bodies that we are considering is the rivet or the bolt and then the steel plate. Okay. If you are referring to the stress by this experienced by the rivet only, then that is the shear stress, which is again the area there is the cross section of this rivet or the bolts. But again, since we are talking about the stress between this rivet and the plate, then that is a bearing stress. Okay. So how are we going to compute? So originally or basically the arrangement or the orientation of the stress is due to the surface in contact. Okay, so what is the surface in contact? If I will try to exaggerate, okay, let's try to exaggerate. If I will pull this plate and then pull the other plate on the other side, on the top, let's just focus on the top plate. Okay, on the plate on the top, what will be the exaggerated deformation of that is that there will be a space here. So what will be the area in contact is only half of the rivet, isn't it? So I will try to rotate that one just like this. This is a clearer picture of that. Okay. So if I will try to exaggerate the failure or the deformation of the top plate on top, I will consider that. Then what will be in contact? Okay, what will be the area in contact between the rivet and the plate is only half of that circle or half of the rivet because the other side will be left blank or space. Okay. However, the distribution of force there experienced by that contact area, okay, because again, the area being stressed or handling the pressure is what we call as the contact area or the bearing area, and which is this one. Whatever is attached or whatever is in contact within these two bodies, that is the bearing area. However, since the distribution of force here, it says there that if you try to read this one, it actually varies from 0 at the edge. Okay, so at the edge of this contact, the pressure is 0. As you go on to the middle, that is the maximum. Okay, and maximum directly at the back of the rivet, or that is exactly at the middle. So again, the distribution of the actual pressure is from 0 at the edge to the maximum at the middle. However, that will be a little bit hard for us to compute. So we are going to simplify it by, okay, equivalent of that, which is a uniform load or uniform stress or uniform pressure, which is equivalent to the projected area. Okay, so instead of calculating that variable stresses from 0 to the edge to maximum to the middle, we will now consider it as a uniform, but the area will now change. Instead of the area, which is this half of the circle inside, okay, which is the actual contact, we will try to reduce that one, get the equivalent projected area. We call that one the projected area. Okay, projected area. Okay, this is the projected area that will now be reduced to a rectangle. Okay, so that is our projected area. So again, the actual scenario is that the stress on this area in contact is variable. But for simplicity and for easier calculation, we will transform that one into its equivalent, which is the uniform, but in this area only, which is a rectangle, the projected area. We call that one projected area. Okay, so that is bearing stress. Okay, so again, as I've said a while ago, we will try to denote that one by sigma sub b to differentiate it from the normal. Okay, so together with your P and A, the P is the force, of course, and then the A is the receiving area, which is the projected. But let's put there sub B, okay, since we are referring here to the bearing. So again, area there is the area, the equivalent of the area in contact, which is the projected, okay, which is simplified for us to be able to solve. So we will now proceed with an example. Okay, so assume that a 20 millimeter diameter rivet joins the plate that are, okay, what's this thing? That are each 110 mm wide, or each of these is 100 mm wide. Okay, sorry about that. Okay, so the allowable stress are 120 megapascal for the bearing on the plate material, and then 60 megapascal for the sharing of the rivet. Okay, let me explain this to you. Why is it that we are considering the failure on the plate if we are referring to bearing. Because if this will snap, okay, if the connection will snap and the failure will happen within the plate, okay, this is an example of this, it will tear within this projected area. It depends, okay, it could tear this way, okay, this dotted line here, or it could even tear at the middle. It depends on the uniformity of the material, okay. So that is the example of bearing stress failure, okay, if we exceeded the bearing stress of the plate. But we cannot say that the bearing stress will have an effect on the failure on the uh, what we call this one, bolt or the rivet, because once this rivet or bolt will fail, that is no longer bearing, that will now be in shear, okay, because the failure will be cross section of the rivet or the bolt. Okay, so the failure of bearing, okay, too much bearing stress will be on the plate or within the projected area. Okay, there will be a tearing, there will be a rupture or a tearing of plate that will happen within that projected area. Okay, so that's why it says there that we will try to control that bearing stress using the bearing strength of the plate materials, because that will be the one to fail if the bearing is too much, bearing stress is too much. Okay, and then of course, if that will not happen, let's say that that plate is very strong, then what might fail there is the connecting material, which is the rivet or the bolt, if that is a bolt. But for us, that is a rivet, so the shearing stress or the shearing strength of that rivet is 16 megapascal. Okay, so first is for us to determine the minimum thickness of each plate, and then the largest average tensile stress in the plate. So first, let's focus on the first unknown, A. Okay, so look at, write down the given. We have there a diameter 20 mm, and then the bearing strength, or yes, bearing strength of the plate is 120 megapascal, and the shearing strength of the rivet is 60 megapascal. But what else is given there is the uh, what do you call this one? Width of your plates. Okay, width of your plates. If you try to look at the figure, it says there that the thickness of the plate is unknown T, and so with the other plate below. So they are of the same thickness. Okay, so if ever that the plate will fail, it's either the top or bottom, it depends, or it could be both at the same time, since the thickness and the type of material of these two plates are the same. So it depends, actually that depends on the uniformity, but supposedly ideally they will rupture at the same time because they are of the same material, the same dimensions, and the same thickness, the same strength. Okay, so therefore we can just consider here one of the plate, and then since we will consider on one of the plate, and then let's multiply the effect by 2, since these are 2, or actually you can just consider 1, because if you try to look at this, okay, this cross section, if I will cut here at this area, there will be 2 areas of plate, which will be a little bit which will be far stronger than if I will cut on the single area of the plate. Okay, so if ever the failure will happen, that will happen at the area of the single plate, not on the double plate. Okay, so that is the weak part of the plate on the single. It's either here or there, not within these 2 area of plates. Okay, so I can just focus on one plate, and then since say equilibrium, if that is force P, then that should be the same force P. So we can focus. So again, let's focus on the first unknown, minimum thickness of each plate. So for us to compute that thickness, minimum thickness, for us to carry that force P, in the first place, we need to know what is that force P. Okay, so what does that mean? For us to evaluate that minimum thickness T, we do not know that force P. So it means that you can increase that force P. But the point there is, we will try to find out the minimum thickness of this plate so that the failure will happen at the same time. It's either on the rivets or in the plate, because if you will have this plate very very thin, then the failure will happen uh, on the plate. Okay, so we will try to maximize so that we will not be wasting the strength of your rivet. Okay, so we will try to find what force P that will fail this rivet, and that force P will be the one to be used to evaluate what should be the minimum T. So that if we will apply that force P that we figure out, then the failure will happen at the same time, so that we will maximize the strength of both of these. Okay, the steel and the rivets. So let's find first the force P. Since your dimensions of rivet is given and the strength of the rivet is given, then we can find the capacity of that, the shearing force P capacity of your rivet. So we only have there one rivet, so the area of that is for one rivet, which is pi over 4 times diameter squared, which is 20. Okay, so again, this is from your shearing formula. Okay, so the strength of the shearing of the rivet is 60 megapascal, and multiply that one with the area. Okay, we just rearrange this formula of shear stress, multiply to the area of the cross section, then you will find the force P that will fail that rivet. Okay, maximize the 60 megapascal, and then that will be equivalent to 6,000 pi, or you can transform that one in decimal, but I'd rather later on use this whole number. Okay, so that the rounding will have no effect, or even if you use this one, the effect will be small, but I want to use still the exact number. So that will be our force P that will maximize the strength of the rivet. Then that will be the one that I will assume to compute the minimum thickness, so that again, if that will fail, at least I maximize the rivet and the plate, so they will fail at the same time, supposedly. Okay, so now I will transfer that force P into your plate. So bearing of plate material, what is the formula? Okay, again, go back there. Shearing or bearing stress is equal to P of that, whatever P is causing that bearing stress of all over the area of the bearing, which is the projected. Okay, so we will try to rearrange. This is your formula, and then substitute that P that we evaluated, and then your sigma is the stress. That is the strength of the plate in bearing. Okay, that is the bearing strength, which is 120 megapascal, and then times the bearing area, which is where we will find the unknown T. So again, how will I find that one? Sorry about that. I forgot to maximize our screen. Okay, well, still, let's try to continue. Okay, so how will I find that bearing area? That is the projected area. Okay, so again, that is the simplified rectangle, which is in the dimension of the, go back there, whatever the area here that is due to the thickness of the plate, and the what is the length of the rectangle, that is the diameter of the rivet, or if that is a bolt. Okay, so that is the area of the rectangle. Diameter of the bolt D times the thickness of the plate, that is the shaded area here, that is the projected area. So if we will try to multiply that one, okay, that is 20, thickness is 20. Sorry, that diameter is 20 times the thickness, which is unknown T. And then play around with this, okay, you will end up with 7.85 millimeters. That should be the minimum thickness in order for us to maximize the strength of the rivet, so that they will fail simultaneously or at the same time. Okay, now second unknown there is the largest average tensile stress in the plate. Okay, so we are now referring to tensile stress. So again, as I've said on the normal, it could be a tensile stress or it could be a normal stress. As long as the area is perpendicular, it is a normal stress. So your B is actually, we are referring here to normal stress. But actually, why is it related to your bearing? Because what we need to solve for this tensile stress, we will need that one from your unknown at A, or from the given here. So that is still related to bearing. Okay, so it says there the unknown is largest area tensile average tensile stress, largest average tensile stress in the plate. Okay, so tensile stress on the plate, or that is a normal stress on the plate. So again, what will be the weakest point of this plate is not within these two, or that is within the single plate. It's either here or there, so I can consider any of that. So if I will try to focus on one, okay, in the one here, look at the top view of that. So if this will fail by means of tension, okay, if this member of this plate will fail by means of tension, where will it possibly fail? Look at this. there are two possibilities. It's either within this full width of the plate, okay, so that will rupture here at this entire width, or using, of course, the our previous knowledge that the lesser the area, the bigger the stress. So in order for us to have a lesser stress, you should increase the area. So the bigger the area, the lesser the stress. So if I will try to cut here, that is a full width of the plate. Compared if I will cut here, okay, look at this. If I will cut here within the alignment of the rivet, then there will be a space which is a reduction on the area of the plate. So if there is a reduction on the area of the plate, then the area of the plate that is handling the force P is smaller compared to the full width here. So which one, based on your judgment, which of these will fail? Of course, the lesser area, because that will be more stressed. Considering that this plate is of the same type of material, the same strength, this will be the one to snap, not the full width. Okay, so that is why we will be using that area instead of the area of the total plate. We will reduce, or we will subtract the area occupied by the rivets. Okay, so again, if I will cut this one, that is a rectangle, but of course, do not forget to subtract the projected area. That is for bearing stress. So the remaining steel here, okay, the remaining steel here on the sides will be experiencing what we call as a normal stress in the type of tension or tensile stress, because the force is tension. Okay, so what will be the area? The force P is steel. Okay, that's why it's related, because the force P, we gather that one on your bearing. Okay, so force P is 6,000 pi Newton. So that is what we will be using for the normal stress. And the area of that is the rectangle. However, we will subtract. Instead of multiplying the total width, we will subtract there, which is 110. We will subtract there the diameter of the bolt, which is, or this rivet, 20, times the thickness, which what we solve on the top is 7.85. So calculating this one will be 26.68 megapascal. Okay, so what does that mean? In this problem, okay, if I want to maximize the strength of this rivet, I need to have a thickness of the plate to be 7.85, so that they will fail at the same time. Okay, the bearing and the sharing will fail at the same time. Now, relating that one with the tensile or the normal stress of the steel member, that will happen within here, which will be equivalent, which will have an equivalent stress of 26.68. Okay, 26.68. Okay, so that is for example number 1. So as you can see, we related your bearing stress with the other types of stresses, which is the previous two, the normal and the shear stress. And then let's try to have two more. So we have here a lap joint, which is fastened by 3/4 inch size diameter rivets. Calculate the maximum safe load P that can be applied if the sharing stress in the rivets is limited to 14 KSI, or that is kips per square inch, and the bearing stress in the plate is limited to 18 KSI or kips per square inch. Assume the applied load to be uniform, distributed among the 4 rivets. So if I will try to apply force P within this connection, both sides, okay, then the force P will be handled by the shearing of these 4 rivets, okay, 4 rivets, or it could be handled by the bearing within the connection, or within the contact of the plate in these 4 rivets. So let's assume that this force P is distributed equally within these 4 rivets. So again, it's up to you if how will you solve this one. If you will consider the 4 rivets, or you will divide the force P by 4 and then consider 1 rivet. So it's up to you. It's your approach. But for this problem, my approach is I will consider the force P and then consider the entire. I will not distribute the force P to each of these. Okay, I will consider the entire rivet and then the entire P. Okay, so thickness of that is 7/8. Okay, given here, by the way, this is not given in the figure, but I mean in the problem, but in the figure it is given to be the thickness of that to be 7/8 inches. Okay, thickness of the plates, they are the same. Okay, so first, let's focus on the base on the shearing of these rivets. Okay, because what we are trying to find is the force P that will fail the connection. So again, we do not know. We do not know. We do not know where the failure will happen. Is that on the bearing of the plate and rivet, or is that on the shearing of the rivets? So let's try to compute how much P the rivet, the shearing of the rivet can hold, or the bearing within this contact of the rivet and the plate can hold. Then let's compare which one is the lesser P. Then that is the maximum P that the connection can hold. Okay. So let's start with the shearing of the rivet. So shearing formula again. Start here. So the force V, which is equivalent to our force P here, is found by multiplying the shearing stress or shearing strength of the rivet times the area of the rivet, which is 4, since they are 4. So the area is 4 times the area of one rivet, pi over 4 times the diameter squared. And then the substitute there, your 14 KSI, that is kips per square inch, and then the area, which is this one, calculate that one, it will give us 24.74. Okay, let me just check that one. 14 times 4. Oh, no, 14, yes, 14 times 4 times pi over 4 times 3/4. Okay, so pi times 3 squared, 126 pi, no. 14 kips. Oh, cancels. Okay, so divide this one by 4 squared. You will end up with 63 over 8 pi, or that is 24.74. Okay, and that is kips because the unit for area will cancel. So that is our force P that will fail the rivets by means of shearing. Okay, so we maximize the shearing strength, and that can only carry 24.74 kips. How about the bearing? Okay, so the bearing again will happen, or the failure of bearing will happen on the plate because of tearing. Okay, that might tear within this one or within the contact of the rivets in the plate. So again, the formula here is given on top. So playing around with that, what is the force P? Okay, that is your P sub B, which is the same as your force P. So the strength for the bearing is 18 KSI. Okay, and the area of the bearing, okay, the same. The area is the projected, but we will still be using the diameter, which is 3/4. So how much area is projected there? Again, the area of one is the rectangle, which is the diameter of the rivet, times, okay, multiply that one with the thickness, which is 7/8. So 4 times the diameter times the thickness, that will be inch squared, and then inch cancels with the inch squared below of this KSI. Then that will be, okay, let me just check that one. 18 times 4 times 3 times 7 over 4 times 8 will be 189 over 4, that is 47.25. So that is uh, how much P the plate can carry before that will fail by means of bearing, okay, bearing stress. So look at this. This is what the shearing can hold. This is what the bearing can hold. So what does that mean? As I increases up to 24, still before this 24.74, none of them will fail. But once I will reach the 24.74, the rivet will already fail by means of shearing. So that is the maximum, okay, that the connection can carry. Because if let's say I will increase up to this 47.25, we cannot do that because the rivet already failed by means of shearing. So how can you increase that one? The connection already failed. Okay, so it means the smallest of this force P is the maximum that the connection can carry. Okay, so that is example number 2. Let's proceed with example number 3. Okay, the connection shown in the figure is subjected to a load P, which is 20 kilonewtons. So this is the connection. That is the load P. And then calculate first is the shearing stress in the pin. Okay, so where's the pin? That is the one holding your connection. Okay, that is our pin. And then we are going to find the shearing stress on the pin, and then D there is to find the maximum tensile stress on the cleaves. So where is the cleaves? This one. This is the cleaves. Okay. Or actually, this entire connection is the cleaves connected by the pin. However, since the dimension of this fixed member where we connected the cleaves is not given, therefore we will base our computation on this given dimension, which is this one, this part of the cleave. And then C, we are going to find the bearing stress on the cleaves, okay, at joint C, or that is within, of course, the contact of the pin and the cleaves. So again, there is no given dimension here, so maybe that is assumed to be stronger compared to this part of the cleaves. Okay, so let's start with the first A, shearing stress on the pin. So just like what we did before, this is load P, and the area that will fail within the pin is the cross section, which is perpendicular to the force P. So what is the area? Of course, that is the area of the circle, which is the caused by the diameter of the pin. So the area for that shear stress is twice, since there are two areas that will fail within your pin. And then the area there is pi over 4 diameter squared. The diameter of that pin is 12 mm. So that will be this area, and then the 72 pi as a whole number. As a whole number. And then the force P is given to be 20. So solving for the shearing stress, multiply this kilonewton, which is 20, into times 10 raised to 3, so that will be Newton. And then the area divided by the area, which is parallel, that is the area of the two cross section, okay, that will fail. Then your shearing stress is 88.419 megapascal. That is the shear stress on the pin. Now let's proceed to B, that is the maximum tensile stress. Okay. Supposedly, the problem should give the dimensions of the entire cleave for us to say that is the maximum. So it means that we will try to evaluate the tensile stress in this part, if this will fail, or maybe that will fail within this part, or maybe that will fail within this fixed part. But since the dimensions of this and that is not given, then let's assume that the maximum will happen here, since that is the only dimension given. But in case this dimension and that is given, then we need to compute and then compare which one is weaker, this part, or that part of the cleave. Okay, so tensile stress. So, okay, so force P over 8. Tensile, if you say tensile, that is a normal stress. So force P, what is the area that is perpendicular? So if I will cut this section, there are two areas, okay? And that is rectangle. If I will cut this one, a rectangle, maybe this form, but without, of course, let's forget first about the projected area. So this length here is this 50 millimeters. That is the width of the cleaves. And then the thickness of this part of the cleave, which is the same as that, is 6 millimeter. So what will be the area is the area of this and that. So the area of 1 multiplied to 2. So 2 times the width of that, which is 50, times the thickness, the cross section of this one part of the cleave, which is 6. So 50 times 6, that is the area of 1 multiplied to 2, since there are 2 of that carrying the force P. Then your force P is multiplied again times 10 raised to 3, so that will be Newton, and divided by the area, you will end up with 33.333 megapascal. So that is the tensile stress experienced by the cleaves, this member of the cleaves. That is the shearing experienced by the pin. And then later on, we will now go here on the last unknown, bearing stress on the cleaves. So look at this problem. We try to consider every type of failure. It's either failure by means of tension on the cleaves, failure by means of shearing on the pin, or lastly, failure by means of tearing on the cleaves because of bearing stress. Okay. So now let's proceed to bearing stress. So again, that's the contact of the pin and the cleaves. So this is the isolated figure for that. So again, just like before. Okay, so what will be the area carrying is the projected area of the contact of the pin and the cleaves. So actually there are two. Since there are two parts of the cleaves connected to the pin, which will be which is in contact with each other, then there will be two bearing area. Okay, so I will be multiplying that, and the area of that is the diameter. Area of one is the diameter of the pin multiplied to the thickness, which is 6 mm. So 12, that is the diameter, times 6 the thickness, that is the projected of one of this part, multiplied to 2, and that is 144 total bearing area. And then divide that one using this area, divide your force P, your bearing will be 138.889 megapascal. Okay, so in case in case you are given the strength of the cleaves in terms of bearing and in terms of tensile or normal, then you can compare. If this will be higher than the strength in terms of tensile of the cleaves, then that will fail by means of tension or rupture because of tension. But let's say the other way, the given bearing strength of the cleave is smaller than this actual stress experienced by that, then it will fail because of bearing or tearing within the cleaves. Or let's say that the shearing stress or shearing strength of the pin is given, and you compare this which is bigger, then the failure will happen within the shearing of the pin. Okay, so that is how we will relate the stresses, actual stresses within the strength. Okay, the strength again is how much stress the certain type of material can carry. It depends on what is that, because the certain type, let's say this is a steel, the shearing strength of steel is different from its compression strength and different from its tensile strength and different from its bearing strength. So this strength of a single material is different. Okay, depends on the type of stress. So that is, for example, number 3. Okay, so that concludes our discussion for unit 3, but let's try to recall the important concepts that we discussed. Okay, the force used in bearing stress can be considered as the normal and the shearing force. So again, the force P in your shearing stress, normal stress, and bearing stress, it could be any, as long as that will be the one to cause the type of stress. Okay, bearing stress uses a projected area for the uniform stress distribution. So as I've said, the actual scenario is the stress varies, and that is distributed on the actual contact area, which is, if that is a circular shape, then that will be half of a circle. Okay, that is the area in contact. So that is where the bearing stress will happen. However, for simplicity, we calculated that one by means of its equivalent, the projected area. And then we will make the variable pressure or variable stress as a uniform stress. Okay, so that is bearing stress. And then the third concept that we need to consider or to bear in mind is the area of the contact in bearing stress is always the contact between two separate bodies. Okay, so the actual contact is where the bearing stress happens. Okay, so that is for unit 3. That is for our bearing stress under your simple stresses module 1. So if you have any question, you can comment below the discussion, or we can discuss that one on the next live meeting. So thank you very much for watching.